All right, let's dive right in. Today, we're putting on our senior consultant hat to map out the engineering requirements for what is, without a doubt, the most critical system in a Formula Student electric car, the high-voltage safety system. And look, this isn't just about following rules. It's about the core engineering discipline that decides if your car ever even sees the track. Let's start with a number, because it tells a very stark story.
40%. Based on years of watching teams at competition, about 40% of brand new Formula Student EV teams fail their electrical inspection. Think about that. That means almost half of all new teams build an entire car, spend all that time, all that money, and it's never allowed to race. From a project management standpoint, that is a catastrophic failure before you've even started. This isn't just a small hurdle, it is the barrier to entry. So we need to completely reframe how we think about this. Building a rock-solid safety system isn't some boring checklist you have to get through. No. From a strategic point of view, it is the engineering that gives your vehicle the fundamental right to exist and compete. Everything else, your slick aero package, your trick suspension, all that power, it's all completely meaningless without this. Okay, so we're going to break this down into two key parts. First up, the brains of the operation. These are the logic-based circuits, the intelligent thinking part of the safety system. And honestly, this is where most of those 40% of failures come from. It's mostly because of one non-negotiable principle we're about to see. They have to be pure, old-school, non-programmable hardware.
Right at the heart of all this logic is the Tractive System Active Light, or the TSAL. You have to think of this light as the car's one and only source of truth about its high-voltage status. The rules are crystal clear here. Its logic must be done purely in hardware. So why the obsession with hardware? Simple. A single line of buggy towed, a microcontroller that freezes up, that's a single point of failure that could tell you the car is safe when hundreds of volts are live. It's a risk you just can't take. Period.
The whole logic behind the TSL is built on what I call a default to danger principle. It's actually really clever. For the system to say, okay, I'm safe, and show you that solid green light, three things have to be true at the same time. The low voltage system has to be on, the tractive system voltage has to be proven to be under 60 volts, and the main high voltage contactors, the AIRs, have to be physically open. But to trigger that flashing red active state, only one of those things needs to be true. If the voltage is high or the contactors are closed, you get red. The system is designed to be paranoid, and that's a good thing. And this design really gets at a critical engineering idea, asymmetric logic. The logic for the danger signal, the red light, is deliberately simple and hypersensitive. It's just a direct measurement right at the inverter. Easy. But the safe signal, the green light, it has a much higher burden of proof. It has to check in with multiple sources, right? The contactor state, the battery voltage, and it's designed to feel safe. If it gets any conflicting information, it just shuts off. Next up in our logic group is the insulation monitoring device, the IMD. The best way to think about this is as your high-voltage system's firewall. Its job, 24/7, is to measure the electrical isolation between all those high-voltage wires and the car's metal chassis. If that isolation breaks down, it means current is leaking somewhere it shouldn't be, and that creates a massive electric shock risk to anyone who touches the car. Now, the industry-standard device here, the Bender IMD, doesn't just give you a simple good or bad signal. It's way more sophisticated. It actually talks to the car using pulse width modulation, where the frequency of the signal tells a story. 10 hertz, you're good, that's normal. 20 and 40 hertz mean other things are going on. But the one you really have to listen for is 50 hertz. That frequency means earth fault. It's a critical failure, and your hardware decoder has to see that 50 hertz signal as an absolute command to shut the whole system down right now. The final piece in our logic puzzle is the brake system plausibility device, or BSPD. Now, this thing is just a fascinating bit of engineering because it's required to be a purely analog computer. Its only job is to prevent a runaway car. Scenario where a throttle gets stuck or a motor controller fails and is demanding full power while the driver is jamming on the brakes. The BSPD's logic is very, very specific. It's watching two things, brake pressure and how much power the motor is drawing. If it sees the driver is braking hard, we're talking over 30 bar of pressure, and at the exact same time the motor is pulling a lot of power, over 5 kilowatts, it starts a stopwatch. That situation just shouldn't happen, and if it lasts for more than 500 milliseconds, the BSPD cuts the power. That half-second window is so critical. It prevents false alarms during aggressive driving, but still reacts instantly to a real problem. And what's more, it's also watching its own sensors. If a sensor fails, it also shuts the car down. Okay, so we've covered the intelligence of the system.
Now let's move on to the brawn, the physical backbone that actually handles all that current, gives you mechanical protection, and carries out the commands from all those logic circuits we just talked about. First up is the high voltage interlock loop, or HVIL. Just picture this as the car's nervous system. It's a really simple, low-voltage electrical loop that's daisy-chained through every single high-voltage connector and every lid on every enclosure. And here's the magic. Every one of those connectors has special pins called last mate, first break pins. So if you try to unplug a high-voltage connector while the system is live, the little HVIL loop breaks first. That instantly tells the system to shut down and open the main contactors before the big high-voltage pins have even separated. It's a brilliantly simple way to prevent a deadly arc flash. Now, the main contactors, those AIRs, they're the big gatekeepers for all that high-voltage power. And which ones you choose is a huge design decision. For instance, a gigawatt contactor uses an epoxy seal, which means you can mount it in any orientation you want, a massive advantage when you're trying to package everything into a tiny battery box. You also have to look at its braking capacity. Can it shut off a huge fault current before your main fuse blows? And think about features like a built-in economizer, which can save a surprising amount of power from your low-voltage battery.
And finally, we've got the core passive components. And here, the rules are absolute. No shortcuts. Your main fuse has to be an EV-rated DC fuse. An AC fuse will not work. It can't stop a DC arc and can lead to a fire. Remember, the fuse is there to protect the wire from melting, not to protect the battery. The manual service disconnect, or MSD, has to give you a clear, physical, visible break in the high-voltage path. And of course, all your high-voltage wiring has to be bright orange and fully shielded to stop electromagnetic interference from messing with your control system.
So we've covered the what and the why. Now let's talk about the how. This is the consultant's blueprint. It's a clear, actionable roadmap to get you from a blank sheet of paper to a car that sails through that electrical inspection. Look, this staged plan is the single best way to take the risk out of your electrical program. In months 1 to 3, it's all about architecture and simulation. You do your failure analysis on paper and in software. Then, months 4 to 6, you build a safety box on a workbench. You have to prove all your logic, your TSAL, your BSPD, works in a safe, low-voltage environment before it gets anywhere near the car. Only after that do you start integrating it into the vehicle, and then you dedicate a full month to being your own worst critic with mock inspections. So here's the key takeaway, the one thing you really need to remember. You can have the most powerful motor and the most brilliant aerodynamics in the entire competition, but all of that incredible performance engineering is completely and utterly worthless if your car is stuck in the garage because it failed its electrical safety check. Performance lets you win the race, but electrical safety, that's what lets you enter it. And that brings us to the final critical question you have to ask your team every single day. As you're designing these systems, are you just building something that checks the boxes in the rulebook, or are you engineering something that is truly fundamentally robust? Because the difference between those two mindsets, well, that's the difference between a team that struggles year after year and a team that builds a legacy of champions.